Okay, we're going to do, let's see if I can get this to focus right. There we go. We're going to go over fall 2017 final exam, question number 11. We're asked to take a look at the series, the sum from k equals 2 to infinity, k to the 1/5, all over k to the 6/5. Okay, so now when I see this, it doesn't jump out at me as any particular series type, so I'm probably going to be able to use some kind of a comparison series. So if I do a comparison series, comparison test, I mean. Okay, so what I'm going to be comparing it to, I need to be able to compare my two highest degree terms. So if I'm looking at k to the 1/5 all over k to the 6/5, that's like saying k to the 1/5 minus 6/5. So this is like saying k to the minus 5/5, okay, which is like saying k to the minus 1, or 1 over k. Because I'm going to be comparing it with this right here. Okay, so when I go to compare it with the sum from k equals 2 to infinity of 1 over k, this is a p-series. And my p-value is equal to 1, which because that's less than or equal to 1, basically this thing is going to diverge. Okay, so I'm comparing this with a series that's bigger than this one, and it's going to be diverging. Okay, so I'm going to say, I'm sorry, it's smaller than that one, and it's going to be diverging. So I'm going to write down k equals 2 to infinity, to the 1/5. 6/5 minus 1 is greater than over k. K equals 2 to infinity. Okay, and I can do some, point by point comparison on that. But because this one diverges, right, by the divergent p-series test, then basically what I can then conclude is that because this one is smaller than that one, and this one diverges, this one is going to push up my unknown series also into divergence. So we can conclude that the thing that we're comparing it to is also going to diverge. Okay, question number 12. Let me write it down so I can see what it looks like. This one says I've got k equals 2 to infinity minus 1 to the k. K ln of k. Okay, so when I'm working on this one here, okay, so when I first look at it, I think, oh, I've got 1 over k ln of k, so it kind of looks like an integral test. But before I go off on that, right, I've got this minus 1 to the k, right? This is telling me that this is an alternating series. Okay, so my alternating series, right, is going to lead me to an alternating series test. Okay, so my alternating series has two different portions to its test. The first one is, I have to check the limit. K goes to infinity. Remember, this is the absolute value, so I'm just checking at k over ln of k. I don't care about the alternating part here. Does this thing go to 0? Yes, it definitely goes to 0. Check. That's my first confirmation. The next part is the k plus first term bigger, smaller than the next one? So we want to basically check out to make sure that this is a decreasing function. So if I go k plus 1, ln of k plus 1, that's definitely less than or equal to 1 over k ln of k. Okay, so therefore, right, these are our two conditions for the alternating series test convergence. Therefore, I can conclude that this series is going to converge, and it's going to converge by the alternating series test. Let me take a look at question 13. Okay, so question 13 says we've got the sum from k equals 1 to infinity, k cubed plus 7 k squared all over 0.2 k cubed plus 13 to the k. Okay, so this one here, basically what I'm looking at is I've got something raised to the kth power. Okay, when I've got something raised to the kth power, that automatically tells me that I should be thinking about the root test. Okay, so I'm going to use the root test on this one. Okay, so the root test tells me I'm going to go the limit as k goes to infinity, I'm going to take the kth root, the absolute value, k cubed plus 7 k squared, 0.2 k cubed plus 13. This is to the k. Okay. When I do this, right, that's going to cancel out these k's here. So then I'm left with, wait a minute, k goes to infinity, k cubed plus 7 k squared over 0.2 k cubed plus 13. Okay, so as k goes to infinity, I'm looking at my highest degree terms, k cubed and k cubed. So I've got 1 over 0.2. So this thing is going to reduce down to 1 over 0.2. Let's think about that one. So 1 over 0.2. This is 1 over 2 over 10, which is equal to 10 over 2. Okay, which is equal to 5. Right now, my criteria for the root test says that if I want it to converge, right, this root test has to be less than 1. Root test will also tell me about divergence. Okay, so if my root test gives me a value that's greater than 1, okay, then I can conclude that this is going to diverge because my value is greater than 1. Look at what we did. We worked on the test that we were using. We worked all the way through with the algebra. We got our answer. We showed what the criteria was, and we gave our conclusion for divergence.